Welcome to demo video of Lab 3 of SNS Lab Manual. In this video, we will discuss about Lab 3. Lab 3 about its title is to explain the properties of different signal types using signal operations in MATLAB. As far as objectives are concerned, display the periodic signal, causal signal, energy and power signals, even and odd signals, deterministic and stochastic signals using MATLAB. Show the results obtained after performing the composite operations on signals, time reversal, time scaling and time shifting in MATLAB. As far as pre-lab discussion is concerned, first of all we go through certain properties of continuous time signals, continuous time periodic signals. A continuous time signal x of t is periodic if there is a positive number t such that if t is the smallest positive value of t for which above equation is satisfied, then t is called the fundamental period of signal. Moreover, if k belongs to z, another expression that denotes the periodicity of a signal is x of t is equal to x of t plus kt, where t belongs to real numbers. For example, a sinusoidal signal x of t is equal to a cos omega t plus theta is periodic with fundamental period t is equal to 2 pi by omega, but t is equal to 4 pi by omega, t is equal to 6 pi by omega, t is equal to 8 pi by omega, etc. are also periods of the signal xt. Sum of continuous time periodic signals. Suppose that x1 and x2t are periodic signals with periods t1 and t2 respectively. The condition must be satisfied in order for the signal x of t is equal to x1t and x2t to be also periodic is given. Moreover, the period of xt is computed. Since x1t and x2t are periodic, we get x1t is equal to t plus mt1 and x2t is equal to t plus kt2, where k belongs to integers. xt is equal to x1 of t plus x2t is equal to x1 t plus mt1 plus x2 t plus kt2, where k belongs to integers. Suppose that xt is indeed periodic with period capital T, then the following relationship holds. Xt is equal to x of t plus capital T is equal to x1 t plus x2 t plus capital T. Combining the equations x1 of t plus capital T plus x2 t plus capital T is equal to x1 t plus mt1 plus x2 t plus kt2. Equation is valid if mt1 is equal to kt2 is equal to capital T, where m and k belongs to z. If m and k are prime numbers, then the period of signals x1t and x2t computed directly according to relationship defined in above equation. Discrete time periodic signals. A discrete time signal is periodic if there is a positive integer number n such that x of n is equal to x of small n plus capital N, where n belongs to integer. A discrete time signal xn is periodic if there are integer positive numbers m, small m, capital N such that omega is equal to 2 pi m divided by capital M divided by capital N. Continuous time and discrete time causal signal. Signal xt or xn is causal if it is 0 for all negative values of time xt is equal to 0 and t is less than 0. Non-causal signals are signals that have non-zero values in both positive and negative time. Finally, a signal that is 0 for all positive time is called anti-causal. Sum of periodic discrete time periodic signals. The sum z of n is equal to xn plus y of n, of periodic signals xn with period capital N1 and yn with period N2 is periodic if the ratio of periods of the summons is rational. That is, here p and q are integers not divisible by each other. If so, the period of Zn is qn2 is equal to pn1. N2 divided by N1 is equal to p divided by q. Even and odd signal sequence. A signal xt is even or has even symmetry or is an even function of t if x of minus t is equal to x of t and t is greater than minus infinity, less than positive infinity, and the same hold for sequence xn. A signal xt is odd or has odd symmetry or is an odd function of t if x of minus t is equal to minus xt and t is greater than minus infinity and less than positive infinity, and the same holds for sequence xn. Then energy and power signals sequence. An important classification of signals is between finite energy and finite power signals. The energy ex of a continuous time signal is computed according to ex equal to this formula, where mode of xt is the absolute value of xt. A signal xt is an energy signal if its energy is definite. The power px of a signal is given by this formula. If xt is periodic, then the power is computed from the relationship. Likewise, the continuous time signals, discrete time signals can also be classified between finite energy and finite power signals. The energy Ex of a discrete time signal is computed according to this formula, where xt is the absolute value of xn. A signal xn is an energy signal if its energy is definite. The power px of a signal xn is given by this formula. A signal xn is called a power signal. Its px is greater than or equal to 0 and less than infinity. In order to calculate the energy or the power of a signal, recall that command limit f, x, a computes the limit of the function f in the symbolic variable x tends to a. Then the second part is signal transformations. Transformations of the time variable for continuous time signals. In many cases, there are signals related to each other with operations performed on the independent variable, namely the time. In this section, we examine the basic operations that are performed on the independent variable. The first operation is time reversal or reflection. The first operation discussed is the signal is reflection. Any signal y of t is a reflection or reflected version of xt about the vertical axis if y of t is equal to x of minus t. The operation of time reversal is actually an alternation of the signal values between negative and positive time. Assume that x is the vector that denotes the signal xt in time t. The MATLAB statement that plots the reflected version of xt is plot minus t, x. A signal xt is called a power signal if px is greater than or equal to 0 and less than infinity. In order to calculate the energy or the power of signal, recall that command limit computes the limit function when the symbolic variable x tends to a. Then the time scaling operation. The second operation discussed is time scaling. A signal x1t is compressed version of xt if x1t is equal to x of at, where a is greater than 1. The time compression practically means that the time duration of the signal is reduced by a factor a. On the other hand, a signal x2t is expanded version of xt if x2t is equal to x of at, a is less than 1. In this case, the time duration of the signal is increased by a factor 1 over a. In order to plot in MATLAB a time scale version of xt, namely a signal of the form yt is equal to x of at, the statement employed is plot 1 over a into t, x. In contrast to what someone would expect, the vector of time t must be multiplied by 1 over a and not a. Then the time shifting operation. A third operation performed on time is one of time shifting. A signal yt is a time shifted version of xt if x of t minus t naught, where t naught is the time shift. If t naught is greater than 0, then the signal y of t is equal to x of t minus t naught is shifted by t naught units to the right towards positive infinity. While if t naught is less than 0, the signal y of t is equal to x of t minus t naught is shifted by t naught units to the left. The time shifting is implemented in MATLAB in opposite way to what may be expected. More specifically, in order to plot the signal, the corresponding MATLAB statement is plot. Now we go towards the Prelab section. In the Prelab section, there are these two tasks, and we will consider them, discuss them, so we may get a better understanding how the tasks can be implemented in MATLAB. So first of all, the Prelab task 1. We write the basic commands: CLC clear all, close all. We know the purpose of these commands. It's better to write these commands in start of every script file. The exceptions are the case of functions, when we do not write these commands, because in this case, in case of normal script, these commands will help to remove the previous data. So now we move towards our Prelab task according to the specific criteria given here. Time is between 0, t is between 0 and 20. We will substitute t is equal to 0, 0.1 is increment, and time goes to 20. Then we have to define x, and for that purpose, x is t into exponential of minus 0.1 t into cos t. And now we write it. X is equal to t dot asterisk cos of minus 0.1 into t plus j into sine minus 0.1 into t. We close the bracket and then again close the second bracket, and now multiply by the term cos t. Cos t1. If we want to see the real part, we can use the command real and pass it argument x. And if we want to see the welcome back to part B of the demo video. In the previous part we were discussing about the Prelab task, and this is the first Prelab task that is open on our screen. We have inserted here, used here the Euler formula, and now we are writing the commands for finding the real part and imaginary part. Now for time reversal, we write here t1 is equal to minus t1 and x1 is equal to t1 dot asterisk cos of cos of minus 0.1 into t1 plus j into sine minus 0.1 into t1 into cos of t cos of t1, yes, cos of t1 cos minus 0.1 into t1 plus j sine minus 0.1 into t1 dot cos t1. F3 is equal to real part of x1, we will name it as x1, and F4 is equal to real part of x2. Now, as written in the manual and the Prelab, first we have to plot the original signal x of t and then even composition and then other parts. As far as the signal xt is concerned, x of t, we can write it here in this way. We are using the subplot command because we will be plotting here multiple graphs. Let's say we use this format. Then we use the plot command p1 t comma f1 comma real r for and then comma p, yes, here we have t, comma f2 comma capital B. We are using these two terms for different colors. And then we can write the command for label title x comma x bracket round bracket and now if we run it, we can name it better to rename it as Prelab task, and here we have, I think, extra bracket, some extra bracket we are having it here, and I think here we need to add an additional bracket. Yes, here we have. Let's try again, and let's say if we insert here bracket, here we have to insert another bracket. Yes, and here we have to insert the multiplying operator, and yes, here we were using t1 for minus t, and x2, yes, here we have to x, we can see it x1, yes, here we have plotted the original signal xt, and we can further also identify the real and imaginary parts. Let's say we use the command legend for separately identifying the real part and imaginary part. Real part, comma, imaginary part, and now if we rerun it, yes, the red line is showing us imaginary part and blue line is showing us imaginary part, and red line is showing us real part. Now the second part, even decomposition. Even decomposition, x underscore e of t, be given here, it is even decomposition of xt. And as far as here, we have to write p2 for in subplot command, two comma 2 comma 2. Then we are defining the signal, it is equal to f1 plus f2 plus f3 plus f4 whole divided by 2. Then we have to plot it, and for plotting we use p2 for subplot t comma x underscore e for even decomposition, and let's say we can give it green color, and then we give it title, and as far as title is concerned, we can write here x underscore e into t and then we can run it. Yes, here you can see we have got the even part, and if we want to plot the odd part, we can copy this and paste it here. For arithmetically, you know, there is small difference of one sign. For decomposition, x underscore o, we can say it is p3 xo. Here the sign will be reversed. First we had minus, we can introduce a bracket here, f1 plus f2, we can also insert bracket here and divide both these by 2, and then we can write it here P3, and we can give it any color, and here we can rename it, and if we run it we can see, we can check for brackets. After F4 there are 2 brackets, unbalanced or unexpected. Yes, if we have to close it here and then again close it here. Now we run it. Yes, here we have the we have to change here a bit of code. Yes, even part, odd part, the original signal, real part shown by red line and imaginary part shown by blue line. This was a discussion about the concepts that are applicable in the lab tasks in the lab task sessions. Further discussion will be carried out during the lab session.